Okay, we are about to look at something that I think is pretty cool. Our last bit of BC calculus for the year. Looking at what's known as polar equations. So it's one of the big themes of Chapter 10, besides the physics feel, is these other functions that are out there, and how do we, do calculus with parametric functions or parametric equations, or vector-valued functions or vector-valued equations, and then how about polar equations? So polar, think of like North Pole, South Pole kind of thing. When you see a polar graph, you'll kind of maybe almost looks a little global to you. They're of the form r comma theta, and r is basically a radius, i.e., distance from origin, whereas the theta is, as you would guess, an angle. And that angle would be found just like in trigonometry, where the starting point for the terminal side, I'm sorry, not the terminal side, but the initial side of the angle would start on the positive x-axis, and you would rotate clockwise as expected. Now, if an angle is negative, you would rotate. I think I just said the direction backwards. It's like trigonometry where you rotate counterclockwise, but if an angle is negative, you would rotate clockwise. If a radius is negative, that just means you would go in the opposite direction. So let's look at a couple examples on a graph. So this would be polar graph paper. You can have your angles marked to whatever degree of accuracy you want. I've seen polar graphs where they just have your typical unit circle angles, like pi over 6, pi over 4, pi over 3. It's nice if you insert the pi over 12ths, because then you've got everything kind of evenly spaced. Of course, everything in between, just like a Cartesian graph. Now, this is really still a Cartesian graph. It's just that the grid is different. So if I want to go, 3 comma 4, well, that means I would go over 1, 2, there's 3 to the right of the center, and then I would go up 4. Now I don't see what vertical units are. Horizontal units I can see on a polar graph, horizontal Cartesian units. I can't see vertical Cartesian units. They might not match up exactly. Well, actually, hold on. 1, 2, 3, 4. I have it about right. It would be right around in here. It would be 3 comma 4. But if we're dealing with a polar coordinate, let me give you an example one. We could have 3 comma pi over 4. So what I would typically do is find the angle and then count out 3 units from that. 1, 2, 3. So right in there, it would be 3 comma 4. If we had 5 comma 2 pi over 3. So I'm going to rotate from the positive x-axis over to 2 pi over 3, but I'm going to count out 5 of these radii units from the center. So 1, 2, 3, 4, 5, and I see it right about there. I need a nice accurate stylus for this, but this will work for now. So there's 5. That newest dot is 5 comma 2 pi over 3. If you were to graph a negative, like I said, so how about 10 comma negative pi over 2? Well, negative pi over 2 would mean I'd rotate clockwise pi over 2. Well, that's 90 degrees. That takes me down to 3 pi over 2. 10 would mean 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 units from the center. That would be that coordinate. What if it was a double negative? So let's say it was negative 6 comma negative 3 pi over 4. So let me find that angle first. Negative 3 pi over 4, this direction. Now 3 pi over 4 is over there at 135 degrees. So negative 3 pi over 4 would be right here. And then negative 6. Now normally I'd count towards that point. 1, 2, 3, 4, 5, 6. So it'd be like right around here. But no, negative 6 would mean you actually go the opposite direction. So it'd be 1, 2, 3, 4, 5, 6. That's where it would be. Right there. So that means that -6 comma -3 pi over 4 would actually be equivalent to just doing +6 comma pi over 4. All right, so you can graph points in the polar direction. It's just a different way of doing it. Instead of, you can get to any Cartesian point the same way, but instead of going left and right, then up and down, you're going an angle rotation and then a distance from the origin. A couple of special graphs. R equals A. So we're going to get into, I guess, a few functions and equations here just a little bit. If you have R equals A, that would be a circle. So let me show you what that would look like. If we just had the graph R equals 7. So R equals 7 means we're graphing all of the points that have a radius of 7. So 1, 2, 3, 4, 5, 6, 7. So that would be, oh my, this is going to be rough making this work around here. Oh, there we go. Oh, I'm off again. Again, I need a better stylus or something here than my finger, but R equals 7, circle with radius 7. The second special graph there, theta equals A. Basically just theta equals a number. That's a line. So if I were to do, for example, theta equals pi over 3, it means graph all of the points that would be having an angle of theta equals pi over 3. So that is that line, all of those points there. If you want to convert back and forth from Cartesian to polar, there's 4 conversions you can use. So sometimes you have to use a little creativity getting the points back and forth, depending on what you have. And you can make it kind of messy, but if you look for a good substitution, you can make it work okay. So there's 4 substitutions that would work. The first one there, x equals r cosine theta, y would equal r sine theta, x squared plus y squared equals r squared, and y over x equals tan theta. And hopefully those all kind of ring a bell just from trigonometry or the Pythagorean theorem. So just taking a quick look at them. Come back here, and let me just pick some sort of arbitrary point out here. So if we kind of think of all of the components of Cartesian and polar, if we're in Cartesian realm, this point we'd go to the right x and up y. But in the polar realm, we rotate that angle theta and we use that radius r. And from there, hopefully you'll see where all of the conversions come from. So first of all, if we were doing our basic trig functions, cosine theta would equal the x coordinate over the r coordinate. Solve that for x, you've got our first converter. Sine of theta equals y over r. Opposite over hypotenuse. Solve that for y, you've got the second converter. Pythagorean theorem is hopefully obvious on the third, right? X squared plus y squared will equal the radius squared. And the last one would be coming from our third main trig function, tangent. The tangent of an angle is equal to the opposite over the adjacent, y over x. So the conversions are pretty straightforward, just as long as you've got some sort of background in trigonometry. The last thing, a quick look at our calculators, and then also maybe an example if we have time here. One would be our calculator. Just want to point out to you that your calculator has a polar mode, just like it has a parametric mode. So if I press mode, there's function, parametric, polar, that last one's sequential. Maybe someday we'll look at that too. So if I go to polar mode and press y equals, well, lo and behold, it's r equals something. So I'll just plug in something here, r equals cosine. Let me press the x button. Wow, a theta comes up. So this is saying graph all of the points. So it's a singular function, like the Cartesian realm. It's not, two functions, x and y, for vectors or parametrics, but this would say graph all of the points where the radius is equal to the cosine of the angle. Well, let's see what that looks like. Well, it's kind of hard to see because it's in there close. So why don't I go back and I'm going to insert a coefficient here. Like, how about a 4? Let's see what that does. We get some kind of loop there. Well, just like parametrics are restricted by the t, polar is restricted by the angle. So that's going from an angle of 0 to an angle of 2 pi. So some graphs, when you, they might just keep tracing themselves. So if you change it from 0 to 4 pi, you just might see the same thing like tracing over itself. But sometimes they'll continue and do some odd things like a spiral or something like that. And again, you can certainly waste lots of time just coming up with different graphs by mixing and matching some different things. And there's sine theta plus cosine theta. A nifty one is really simple. If you do r equals theta, there's one where the coordinates, or I'm sorry, where you can change your theta interval for something interesting. So if I hit graph, get a little spiral here. Okay, that was a pause to sign a permission slip. But anyway, you've got a spiral here. Press window. I can alter this. Let's make it 20. And graph. And it's just going to spiral off the screen. Now think about what it's doing. It's saying the radius is equal to the angle. So that means when you go to an angle of pi over 2, you're pi over 2 units from the origin. And if you look, it does kind of look like that. Like pi over 2 would be right up here on the positive y-axis. And pi over 2 is about 1.5, so that's why it's at 1.5. When you go to pi, there's your angle of pi would be over here to the left, and you're about 3 units from the origin. So each angle becomes a farther rotation, or a farther value from the center. Okay, for time's sake, I think we will save some of the converting for in class. But again, your converters are right there. And we'll look at taking some Cartesian equations, turning them polar, and vice versa at a later time.